Okay, so let's take a look at how that variance decomposition works in the context of two little example random variables that I've come up with to illustrate this business of the variation within groups defined by Y and across groups defined by Y. Okay, so I'm not going to work through every step here. I'd encourage you to do that, to check all the numbers throughout here. We're going to do a similar thing in workshop as well. But what I want to do is sort of take you through the big picture and hopefully give you a sense of why we care about this variance decomposition. Okay, so what I've done is I've created two random variables, and by that I mean I've just made up this part of the PMF. I've made up the probabilities assigned to pairs of values of X and Y. Okay, so I've done it for one that I'm calling Y, XAYA, and XBYB here. Okay, and so that's kind of the thing that we're starting with here. We're starting with joint probabilities for x equals 0, y equals 0, x equals 0, y equals 1, etc. And from that, we can add across columns and rows to get the marginals. We can calculate the unconditional expected value and the unconditional variance. We can do both of those things. And we can find the conditional PMFs. Okay, so when finding the conditional PMFs, what we've got here is this is just the probability, joint probability that x is 0 and y is 0 divided by the probability that y is 0. Okay, so this is the way we're always calculating those conditional probabilities, the joint divided by the probability of the conditioning event. Okay, so I'm going to erase that so I can look a little more closely at these. So I've calculated the probabilities of x conditional on y being 0 and y being 1. And here I want to draw your attention to a couple of things. Okay, there's a big difference here across the two columns. Okay? If y is 0, x is likely to be itself 0. 90% chance that x is 0. If y is 1, very different. Here, x is likely to have its highest value, 0.8%. Okay. The other thing that you might notice is there's not a huge amount of variation within the columns when you have one outcome being 90% likely, one being 80% likely. That's not as much variance within the values of y as when you have numbers closer to equal there. I've lost my video, so I'm going to stop. I can stop the recording for a minute and make that behave. I'll be right back. Okay, I think we're back. So where was I? I was noticing that on this side, for the XAYA random variables, there is big variation across y and not so much within y. Okay, so this random variable is one where if we know the value of I, we're like actually pretty certain about x. Okay, knowing the value of y is really helpful here. Like let's compare that now to the other column, another set of joint probabilities here, calculated the marginals, calculated the unconditional variance, calculated the conditional PMFs the same way. So the probability function for x conditional on y equals 0 and y and conditional on y equals 1. And what you see here is there's actually, in this case, not much variation across y. The columns are like really pretty similar, okay? And there's lots of variation, or as much as there can be with just 3 values, within groups of y. Okay? And indeed, you see both of the conditional variances are pretty small here, and they're much larger here. You can also see that the difference between the two expected conditional expected values here is not very great, and here it is, close to 0, close to 2 there. So this is the kind of random variable we would say that A is where most of the variation is across values of y. This is one where it's within values of y. And so the rest of the calculations here are just meant to show you how that works out into those two terms on the right side of the law of total variance. Okay, so just kind of continuing down the first column here, I've got my two conditional means, conditional on different values of y, and the two conditional variances here. So let's take that conditional mean and treat it like a random variable, like we said we could. And what that, let's call it z to help us not be distracted by the fact that those numbers are conditional means. Z is just a number that takes value 0.1 with probability 0.5, probability that y is 0, and it takes value 1.8 also with probability 0.5, probability that y is 1, and the expected value of this z is 0.95, and we can calculate its variance too of this z, and we get that number. We can also do the same thing for the variance. If you wanted to, you could say let WA equal the variance of XA conditional on YA here. And what that means is that WA would take value 0.9 with probability 0.5, this is a 9, and 0.16 with probability 0.5. So I'm just doing the same thing here with the variances. I'm saying they're just numbers. They constitute the two outcomes of a random variable whose probabilities are determined by y, and I can find the expected value of this number of my w here the same way I always do. 0.9 times 0.5 plus 0.16 times 0.5. If we wanted to just like go crazy, we could calculate its variance too, but praise the Lord, there's no variance of the conditional variance in this term, this expression to worry about, so we don't need to do that. But what we have now here is we have the three components of the law of total variance. Okay, we have the unconditional variance. We have, maybe let me do a different color here. We have the variance of the expected value here, and we have the expected value of the conditional variance. Okay, and the variance of the expected value tells us how much of the when it's large, it's telling us that a lot of the variation is within the groups of y. And I just said it backwards. When this variance of the expected values is large, when what we expect about x given the value of y has a lot of variance to it, it means that the variation across the values of y across, let's highlight it with the right color here, is the larger number. Okay, expectation of conditional expectation of x, what we think about x conditional on y, has a high variance because it's really different. Use the same yellow here. across the two values of y here. Okay. All right, and so then, not surprisingly, random variable b has the opposite pattern here. We go through that same process here, and we calculate the variation across the groups of y, and we get a really small number here. And when we calculate the variance within groups of y, okay, the expected value of the variance within the groups, that's a pretty big number. And this is telling us that most of the variance is within the groups defined by y. And again, that's what we see here, that there's a lot of variance within the columns, sort of relatively even probabilities assigned to the different values, not a lot of variation across the columns here. Okay, so this is a little example that I cooked up where we knew like the whole PMS, we knew everything there was to know about these random variables because I made them up. But what the cool thing about this decomposition that the law of total variance lets us do is it helps us find these values from just from the conditional moments. So, as I said, this is one of the, I would say, most advanced topics in 200A. I'm just kind of throwing it at you and letting it set. Don't stress about it. You're going to hear about it again, but hearing about it now is going to help you be a little less overwhelmed when you encounter it in 200B and classes beyond that.